statement of second law of a thermodynamics. So what this law is going to indicate? So this law is going to state that this second law of thermodynamics has been enunciated meticulously by Clausius, right? Clausius, and another person is Kelvin and Planck. Kelvin and Planck is slightly Kelvin and Planck is slightly, that is Kelvin Planck statement. We can call it as a Kelvin Planck statement and Clausius statement, right? So Clausius statement and another one is Kelvin Planck statement, right? In slightly different words. See, observe this. Words are different here, although both the statements are basically identical. So each statement is based on irreversible process. So that you should have to understand. Each statement it is based on the irreversible process. So the difference between the reversible process and irreversible process, that the basic concepts we have covered in the first unit. So recapitulate that particular first unit basics. Now here the first what you have to consider is that so the transformation of a heat between the two reservoirs. So the transformation of heat between the two reservoirs means, if you observe, this is the engine and this is the sink. This is the source which is maintaining at a temperature T1. Sink is maintaining at a temperature T2. The transformation of heat, that is Q1, and the heat is rejecting to the sink Q2. And here you are going to get the network output. So the transformation of a heat between the two reservoirs, while the second one considers the transformation of a heat into work. The second one is, that is the second statement is focusing on the second statement focused on transformation of a heat into work, and the first one focuses on the transformation of heat between two reservoirs. So the first one is transformation of heat between two reservoirs. Second one is the transformation of a heat into work. So that is what these two statements are going to discuss. So then what is the Clausius statement definition? So the Clausius statement definition is nothing but it is impossible to construct a device, or it is impossible for a self-acting machine working in a cycling. So this is the cycle. So this is the cycle, right? So this is the cycle. Self-acting machine working in a cyclic process unaided by external agency to convey the heat from a body at lower temperature to the body at a higher temperature. So always heat will flow from high temperature body to the low temperature body. If you want to transfer the heat from low temperature body to the high temperature body, some external input is required. Some external input is required. So without that external input or external agency or external device, it is not possible. So that is what the Clausius statement. So it is impossible to construct a device operating in a cycle produces no effect other than the transfer of heat from lower temperature reservoir to the higher temperature reservoir. In other words, heat of itself cannot flow from cold body to a hotter body. Heat itself cannot flow from cannot flow from cold body to the hotter body. Right? So that is the Clausius statement. What is the Kelvin Planck statement? It is impossible to construct a device or engine. It is impossible to construct a device or engine while operating in a cycle produces no effect other than extracting heat from a single reservoir and do equivalent amount of a work. That means what is going to indicate that it is impossible for a machine to produce the network output, right? It is impossible for a machine to produce the network output by exchanging heat with a single reservoir, right? So this is what the Kelvin Planck statement. So according to this one, what it is that if an engine has to produce the network output, it has to exchange the heat between the source and the sink. This is what. So Kelvin Planck statement states that it is impossible to construct an engine which while operating in a cycle, this is the cycle, operating in a cycle produces no other effect except to extract the heat from a single reservoir and do equivalent amount of work. So in simply, what I tell you that not possible to produce the work by exchanging heat with a single reservoir. So that is the meaning of a Kelvin Planck statement and Clausius statement. Kelvin Planck statement and Clausius statement. So hope these particular statements are clear. So once these statements are clear, then you can easily prove that these two statements are one and the same. These two statements are one and the same. That is what the second law of thermodynamics is going to discuss. So though the authors are different and their words are different, but they are proving that the two statements are parallel statements to the second law of thermodynamics. So the efficiency of heat engine we used to write as efficiency is equal to W net divided by Q1. So that W net is nothing but equal to this W net is nothing but equal to Q1 minus Q2 divided by Q1. So this you can write it as 1 minus Q2 by Q1. So the experience shows that when the W net work is less than the heat supplied, since the heat Q1 is transferred to the system, cannot be completely converted to the work in a cycle. So therefore, the efficiency is less than unity, or the efficiency is less than 100%. Right? So heat engine can never be 100%. Therefore, Q2 must be, that means whatever the heat is rejected, that heat rejection must be greater than 0. There has always to the heat rejection. Then only you can get the net work output. Whenever there is a heat rejection is there, then you can get the positive work output, right? So to produce the net work in a thermodynamic cycle, a heat engine has to exchange heat between the source and the sink, right? So Kelvin Planck statement of the second law, it is impossible for a heat engine to produce network in a complete cycle if it exchanges heat only with the bodies at a single fixed reservoir. So that is what it is already covered. So next thing is how to prove these two statements are equivalent to each other. So everyone has to think onto this particular, yes, whenever there are two statements are there, then you have to, how you are going to prove that these two statements are equivalent to each other. So that means when you violate one statement, the other statement is also going to violate. When you violate one statement, the other statement is also going to violate. So what is that the other statements here? What it is going to discuss? So first thing is you have to assume. You have to assume that a cyclic heat engine, assuming, see here, this is the more powerful word here. Let us assume a cyclic heat engine. This is the cyclic heat engine. Heat engine operating between the same thermal energy reservoir. So this is the T1 and this is T2. This is T2. Producing network in one cycle. The rate of working of the heat engine is such that it is going to draw the Q1 heat and producing the network output by exchanging or by rejecting some amount of heat which is greater than 0. So the rate of working of heat engine is such that it draws an amount of heat Q1 from this source from hot reservoir equal to that discharged by the heat pump. The hot reservoir may be, now here you are assuming that this is the case. That is, here you are assuming that heat is transferring from the this particular case to this particular. Now what you have to assume that here, what you have to do that there is a heat pump. The heat pump is also operating between the sink and the source. Sink and the source. The heat pump job is it has rejected the heat to the hot reservoir. The heat pump job is nothing but it has to reject the heat to the hot reservoir. That means here let us assume that a heat pump is operating between the source and the sink, and this is transferring the heat from low temperature body to the high temperature body with zero work input. So that means here whatever the heat input is rejected by this heat pump, and it is this heat engine is taking, then what is the necessity of this heat reservoir? Now I am going to eliminate this one, right? So directly I will make a connection like this one. What is the necessity of this heat reservoir, hot reservoir? So if you eliminate this hot reservoir, then a heat engine is producing the network output by exchanging heat with a single reservoir. See this one. That means this is neglected or this is removed, and the heat engine is producing the network output by exchanging heat with a single reservoir. So this is also going to violate. So violation of a one statement is going to lead to the violation of the other statement. Violation of a one statement leads to the violation of the other statement. So here also the heat pump. The heat pump is operating in a cycle that is in between the source, in between the source and in between the sink. So this is the sink, right? In this particular. Now here, what is going to happen that Q1 plus Q2, the heat engine is this one, that is a heat rejection is 0, assuming that the heat rejection is 0 and it is producing the work out. So this is to be given the heat input to this one. Now this is going to be here. So here the heat rejection is there and producing the net work out. That means this is going to be operating in this particular side. So here first thing is the assumptions. You have to write the assumption. So let us assume that this is going to be operating between the source and the sink. Now whatever the heat rejected by the sink or whatever the heat rejected by the source, then what is the necessity of maintaining one more reservoir here? So one more reservoir means it is going to, if you are, that is, this is a violation of the Clausius statement. So this is violation of the Clausius statement. What is the Clausius statement, right? So violation of a Clausius statement. Heat is transferring from low temperature reservoir to the high temperature reservoir with zero work input. What is the violation of a Kelvin Planck statement? Heat is transferring, heat is exchanging with a single reservoir and producing the network output, and the heat rejection is 0. So these two are going to be violated, right? So that the student has to understand in this particular statement. So the violation of a one statement is going to lead to the violation of the other statement. If you can do that one, then it is going to do this one. So prove that violation of a Kelvin-Planck statement leads to the violation of a Clausius statement. So what is that here? If you just observe that in this particular sketch, the refrigerator is transferring the heat from low temperature reservoir, that is QL is nothing but equal to Q2, right? And it is rejecting the heat QH, that is this is rejecting the heat Q1 to this high temperature reservoir, right? So whatever the heat is rejected, and this heat is taken by this heat engine. Now the heat engine is, whatever the work output from the heat engine is there, it is taken by this one. But here this Q2 is, here Q2 is 0, right? So this is a refrigerator that is powered by 100% efficient heat engine, right? And the refrigerator, so this equivalent of a refrigerator. So violation of one statement is leads to the violation of the other statement. Then that particular things are become proving that particular statements are very easy. Otherwise, it is going to become the difficult. So next, the another thing is the performance of the refrigerator. So how you are going to mention the performance of a refrigerator? Always the performance of a refrigerator you will mention in terms of energy efficiency rating, right? So the performance of a refrigerators, air conditioners in the United States is often expressed, they will often express in terms of energy efficiency rating. That means this energy efficiency rating is nothing but amount of heat removed from the cold space in BTU, that is British thermal unit. BTU is nothing but British thermal unit for 1 kilowatt hour. So the amount of heat removed from the cold space in British thermal unit for 1 kilowatt hour of electricity consumed, then considering 1 kilowatt hour is nothing but equal to 3412 British thermal unit, and thus 1 watt hour is nothing but equal to 3.412 British thermal unit. and this unit that removes 1 kilowatt hour of heat from cold space for each kilowatt hour of electricity. So it is going to consume COP is equal to 1. So when COP is nothing but when COP is equal to 1, then the energy efficiency ratio is nothing but equal to 3.412. That means the energy efficiency ratio is equal to 3.4 times the coefficient of a performance of a refrigerator. Right? Energy efficiency rating is generally mentioned as a performance parameter in the United States for air conditioners and heat pumps. So that energy efficiency rating is equal to 3.4 times the coefficient of performance of a refrigerator. So most air conditioners will have the energy efficiency rating as in between 8 and 12. Then what about the COP of a air conditioner? The COP of air conditioner is 2.3 to 3.5. So a high efficiency heat pump manufactured by a Train company using the reciprocating variable speed compressor is of 3.3. So that means a heat pump, for the heat pump, the efficiency, that is high efficiency, that is energy efficiency is of 3.3 heating mode, and EE of 16.9, that is COP in the air conditioning mode. So this is the difference between the air conditioner and the heat pump, air conditioner and the heat pump for the different situation. So that is the difference between, that is the distinction between the coefficient of performance and the energy efficiency rating. So in Indian climate, most of the times we used to mention it as a coefficient of performance, whereas in the United States, they generally used to prefer for the energy efficiency rating of that particular machine. Right? Hope these particular things are clear. So the energy efficiency rating or COP of a refrigerator decreases. See, observe. Energy efficiency or coefficient of performance of a refrigerator decreases with a decreasing refrigeration temperature. Therefore, it is not economical to refrigerate to a lower temperature than needed. So the COP of refrigerators are generally in this 2.6 to 3. The COP of a heat pump lies in between 3 to 3.5. So that you have to observe. So one value which is greater than this one, because already we have learned that COP of a heat pump is nothing but equal to COP of a refrigerator plus 1. Right? So this is what, so note that COP of a freezer, that is freezer, COP of a freezer is about half of the COP of a meat refrigerator. Right? So, and it costs twice as much to cool the meat products with refrigerated air that is cold enough to cool the frozen food. So, it is good energy conservation practice to use a separate refrigeration system to meet the different refrigeration needs. So, this is more important. So we should not use the same refrigerated machine for all the purposes or for all the applications. So if you are using or if you are doing like that one, you need a penalty. That means you need to maintain the high power bills for that particular cases, right? And the life of that particular machine is also going to damage. So these are the things that every student has to observe. And there are the simple problems are there. So that is you can calculate, that is by reading this particular thing. So there is a thermal efficiency you need to find. So this thermal efficiency is equal to Q1 minus the Q2 divided by Q1, right? So this is nothing but equal to network output divided by the heat supplied. So try to check it out, and efficiency, thermal efficiency you will get for this particular answer is 37.5. 37.5 percentage. 37.5 percentage. The efficiency for this case is 37.5 percentage. So try to observe this answer, because all the things we have discussed. So it is from your end, you need to check whether how much content you have received by studying the various parameters of a heat engine, heat pump, refrigerator, right? So next one is the food compartment of the refrigerator. and it is maintained at 4 degrees centigrade by removing the heat at 360 kilojoule per minute. If the required power input to the refrigerator is 2 kilowatt, determine a coefficient of performance. Coefficient of performance of a refrigerator is equal to the desired effect is Q2 divided by Q1 minus Q2, or in some other words where you can low temperature, because this is the QL sink side. So Q1 minus Q2. This is nothing but equal to Q2 divided by work input. Q2 divided by work input. Or in terms of the temperature, say the temperature, say suppose sometimes the coefficient of a performance of a Carnot refrigerator. So in that case, T2 by T1 minus T2. That is nothing but T2 divided by the work input. So these are the things you have to use. So the Carnot. So in case of a Carnot cycle, then you have to use the temperature, right? So related to that one, find out the refrigerator, and that the COP of a refrigerator, you will get this one as the answer is, you will get the COP of a refrigerator as 3, COP of a refrigerator as 3, and the other one, that is the rate of heat rejection to the room that houses the refrigerator, right? So that is the Q1, that is nothing but equal to QH, and you will get that answer as that is the QH is nothing but equal to QL plus work input. Then this is nothing but equal to Q2 plus W. So from this case, the answer is 480 kilojoule per minute. So this is the answer. Try to check it out from your end. Kilojoule per minute. Units is kilojoule per minute, because here this Q1, right? Already removing the heat. This is given. So related to that one, try to use the basic fundamentals and get the answer. So this is the refrigerator part. This is the refrigerator part. Next, the part is going to be covered for the heat pump. So how you are going to solve the heat pump application? So how you are going to solve the heat pump application for this particular site? So now come to the heat pump. So the heat pump, this is the heat pump used to meet the heating requirement of a house. So here the efficiency formula, that is COP of a heat pump, that is equal to the desired effect is Q1. Observe that is from the diagrammatic sketches from the previous case, divided by work input. Say suppose if it is a Carnot coefficient of a performance of a heat pump. So in that case, you have to use it as a T1 by T1 minus the T2, that is equal to R Q1 by Q1 minus Q2, or it is QH divided by Q1 minus Q2. So these are the things you have to observe. And when you solve this particular case, where the first thing is you need to find out the power consumed by the heat pump. So the power consumed by the heat pump, that is the W, you will get it as a 32,000 kilojoule per hour. 32,000 kilojoule per hour, because the COP is already it is given. COP is 2.5, it is given 32,000 kilojoule per hour. And the second bit, that is the rate at which heat is absorbed from the cold outdoor air. So for this particular cases, QL is equal to QH minus W work input. So you will get the answer as 48,000 kilojoule per minute. Kilojoule per, sorry, it is a kilojoule per hour. So kilojoule per hour. So this is what you have to use, right? So, and for heat pump, draw the diagrammatic sketch. Refrigerator, draw the diagrammatic sketch. And heat engine, draw the diagrammatic sketch, so that you can easily solve that particular problem. Okay. So these are the numerical problems connected to the heat engine, refrigerator, and the heat pump. So the purpose of a heat pump is maintaining the room temperature higher than the outside environmental conditions, outside environmental temperature. So that is nothing but the heat pump. So these are the summary, that is there is a limitation is there. So what is that limitation? So all the work can be converted to, say here, all the work you can easily convert into the heat, but you cannot convert, that is, though you are giving the same heat, whatever the thing it is going to get, you cannot get the no work output. So that is the limitations of the first law of a thermodynamics, right? And there is a, when two Carnot engines are operating between the source and the sink, if this is rejecting the 80 kilojoules and this waste heat is rejecting 70 kilojoules, and the heat input will be the same, the efficiency for this case is 20%, the efficiency for this particular case of a machine is 30%, right? So this is how the problems are there to this particular end. So that is the and the another examples, that is say few things are there. See this one. So the heat pump, and what is the final concept? The concept of a reversible process, leads to the definition of the second law efficiency. Concept of a reversible process leads to the definition of a second law efficiency for actual process, which is the degree of approximation to the corresponding reversible process. So this enables us to compare the performance of a different devices. What are that one? Refrigerator, air conditioner, and heat pump, right? So what is the energy efficiency rating of the refrigerator, energy efficiency rating of the air conditioner for the same heat input conditions or for the same heat rejection condition, right? So that are designed to the task. The better the design, the lower the irreversibilities and higher the second law efficiencies. Higher the second law. That means whatever the irreversibilities are present in the system, that engineer has to minimize that particular irreversibilities. In a system, engineer has to minimize these irreversibilities so that the second law efficiency is going to improve. Second law efficiency is going to improve. So this is what all about the for today's class. That is the second law and its importance. Why to study the second law, and what are the limitations of the first law of thermodynamics, and what are the performance parameters of a heat engine, refrigerator, heat pump, and air conditioner. So thank you, one and all.